camera. Please turn on your camera. And administrator, take a photo. No, this is by me.
You can take a photo? Just copy the screen, I think.
Okay, I will take a photo now. 1, 2, 3.
Please turn on the camera, everyone. Only few people turn on the camera, I think.
Only, okay. Okay.
So, anyone who just recently joined, it is the photo session. So, we encourage you to open your camera and let's take a photo together. All right.
Okay.
Okay.
2, 3.
1, 2, 3. Thank you so much. Okay. So,
Okay, thank you. So I would like to share my slide. So can you see my screen?
Yes.
Okay, thank you. So this is the 16th incubator session towards the social application of the ocean data. Sorry, I cannot read. Data assimilation and forecast potential contribution to the ForeSea and CoastPredict. So motivation is session to share understanding usefulness of ocean data assimilation and prediction systems and to create a collaborative relationships to use the system for the achievement of the SDGs. So we have 4 talks to introduce data assimilation systems at each countries and 2 17-minute talks to introduce international project, the ForeSea and CoastPredict. And lastly, at last, we have a 40-minute discussion part. So the first speaker is me. So the title is the Regional Ocean Data Assimilation Systems in Japan. So first, I would like to introduce the importance of the ocean predictions. The marine heat waves, the high SST associated with the marine heat waves leads to the coral bleaching recently often observed. And also the strong coastal current from the offshore to the nearshore directions across the strait have a significant damages on the aquaculture raft, as shown in this figure. And recently, the Japan televisions broadcast the pumice, the light stones formed by the eruption of this eastern side of the submarine volcanoes have significant damages on the coastal regions in the Okinawa Island, as shown in these pictures. The light stones covering the coastal area and damages on the marine environment. So thus, ocean prediction could contribute to marine environment, fisheries, and marine transport. The accurate data sets are required for the ocean prediction and monitoring. So I would like to introduce what the data assimilation is. The data assimilations can optimally combine between the simulations and observations with statistical methods and dynamical system theory. So this is a snapshot of the sea surface temperatures. The ocean simulations provide a 3-dimensional homogeneous grid, but this is not accurate. This is confirmed from the SST difference between the simulation and observations. So we can see the 2 degrees Celsius higher SST because of the error growth over the time. On the other hand, observations provide accurate values, but the distribution is sparse and inhomogeneous. Again, in the data assimilation, can play a role in combining the optimally between the simulation and observation using the statistical method and dynamical system theory. So we can see the small SST difference between the data simulation run and observations. Thus, the data simulation provides a more accurate dataset without missing values. So this dataset can be used for the initial conditions for ocean predictions and ocean monitoring. So again, the motivation of this session is to share understanding the usefulness of ocean data simulation and prediction systems, and to create collaborative relationships to use the system for the achievement of the SDGs. So I would like to explain the dataset, what kind of the dataset can be used for the ocean data simulation systems. The 3D bar, 4D bar has the advantages to add the constraint to reduce the initial shocks. The Kalman filter, ensemble Kalman filter is also used for the ocean data simulation system, and Kalman filter has the advantages to be appropriate to perform the ensemble predictions. So this table summarizes the number of the analysis products over the global domain. So we can see that the 3D bar system is most commonly used among this data assimilation method, and there is no ensemble Kalman filter based dataset. Unfortunately, Japan has a high resolution regional analysis product at each assimilation method in the North Pacific region. The Jacob 3D bar system, Jacob2 from Jamstack, and 4D bar system, movemri.com from the MRI, and Kalman filter system, Dreams from the Kyushu University, and ensemble Kalman filter system, Lola from Riken. So today I would like to introduce these systems and activities in this talk. So first, I would like to introduce a 3D bar system, Jacob2 from the Jamstack. This Jacob2 is now downscaled from the global to local scales, as shown in this figure. That is a 10-kilometer grid to the 200-meter grid. In the inner system, with a 200-meter horizontal resolutions, show the complicated flow structure and strong tidal mixing compared with the outer system with 3-kilometer horizontal resolutions. So now this Jacob2 group provide near real-time ocean current predictions to shipping companies through this tablet on the bridge. This contributes to the reducing the fuel usages and CO2 emissions. Next is movemri.com from the MRI. This system is a new operational ocean forecasting system since October 2020. And this system contains the outer system, the NPR 4D bar, and inner system, JP and IAU. The outer system has a horizontal resolution of the 10-kilometer in this large domain, and implemented with a 4D bar assimilation method. The target is a method scale variation in the open oceans. And JP and IAU system, as shown in the right figure, have a horizontal resolution of the 2-kilometer, and tide and SLP effects is included. And this JP and IAU system use a temperature and salinity increment derived from the NPR 4D bar system, and the target is a coastal sub-method scale variations in the coastal oceans. The JP and IAU system in a system captures the near-shore sub-method scale variation as shown in this figure, such as the coastal trough waves. The high sea level anomaly is propagated along the coast in the eastward direction as shown in this figure. And high-level sea is also, high-level sea and strong ocean current is also reproduced in this JP and IAU system as shown in this figure. This is related to the approach of the Kuroshio south of the Japan. Now they are prepared to be provide this predictive information for the local fishery organizations. The information includes a current map and forecasted maximum speed. So next is the dreams from the Kyushu University. But this dreams is also downscale from the basin scale to local scale. That is 20 kilometer to the 1.5 kilometer horizontal grid. They now established a project collaborated with a private company, Jeffrey Advantech and Fisherman. The Jeffrey Advantech private company in Japan invented the new CTD easy handling for the fishermen. The fishermen use this smart ACT to observe the temperature profile. This is the temperature profile accumulated by the fishermen in 1 month. And the DREAMS groups conducted a sensitivity experiment with and without assimilation of this temperature profile. The blue is without assimilation, and red is with assimilation of this profile. So we can see the significant velocity improvement by the assimilating the CTD data. So this prediction information is provided through this Android applications. This means that this Android applications connect between the researchers and the fishermen. Actually, the DREAMS team received a positive comment from the fisheries. Actually, the 50% saving the fossil fuels and work hours.
5 minutes.
Okay, thank you. The last is Laura from the RIKEN. The LoRa is an ensemble Kalman filter-based ocean data assimilation system newly developed in RIKEN, will be released in 2020 next year. This system contains the 2 domains, Western North Pacific and maritime continent regions with horizontal resolution of the 0.1 degree. Now we conduct an intercomparison analysis of this among these data sets. This is the RMSD in the donor velocity relative to the surface trajectory. So we can see this RMSD difference map shows the RMSD has a better accuracy in the mid-latitude regions, and JCOP2M has a better accuracy in the subtropical regions. And Abysso has a better accuracy almost over the domain in the North Pacific regions. However, in the maritime continent regions, the LoRa has a better accuracy in the coastal regions, and Abysso has a better accuracy in the open ocean regions. Thus, the LoRa appears to have a good accuracy in mid-latitude and coastal regions. So finally, I would like to introduce the Japanese venture company Oceanized. The President Yusuke Tanaka, the panelist of this discussion part, founded this venture company is called the Oceanized. They construct a 4 coastal data assimilation system based on MoveMRI.com and DREAMS, covering this coastal region around Japan with a 1.7 kilometer resolutions. They are now provide a special map in temperature, chlorophyll, velocity through this Fisher Navi on the website. And in future, they would like to, will release the potential fishing grounds for the fishermen. So I would like to summarize my talk. So fortunately, Japan has 4 ocean data assimilation system, data assimilation and prediction systems. And now, most of the data assimilation system is downscaled to capture the nearshore variations and make a collaboration with the shipping companies and fisheries, and providing the information through the mobile devices and website. And we are now conducting intercomparison of the accuracy among these systems. So lastly, finally, I would like to suggest a possible feedback between the researchers and the users and stakeholders. So researchers can provide a prediction to the users and stakeholders through this Android application and tablet access. And users and stakeholders, if the users and stakeholders can observe, provide insight observations to the researchers could provide better predictions to the users and stakeholders. I think that our goal is to build such a positive feedback to achieve the SDGs. Yeah, thank you for your attention. Any questions or comments? And questions, I welcome questions not only from the researchers and users and stakeholders.
So which shown? So
Yeah.
this ensemble-based assimilation scheme, exactly which data assimilation scheme is used?
LETK.
Okay. And the model? Which model? Which ocean model?
SBPOM, the Princeton Ocean Model.
Okay.
So I combined I implemented this LETK with this SBPOM. And the detail of the setting is not shown here, but the assimilation interval is 1 day, and almost observational data sets, including the satellite and insight temperature and salinity, is used for the assimilations.
Thanks.
If any other questions?
Sure, and it's Emlyn Jones here. I've got a question if we've got time.
Okay.
Have you guys started working on preparing the assimilation systems for SWOT, given that SWOT's likely to be coming online towards the end of next year or early 2023? And have you started playing around with assimilating SWOT tracks in the presence of tides in your area?
Sorry, so lastly, I cannot hear your questions. So the SWOT can be used for the, will be used in next or the next year, I think.
Okay, and are you assimilating in the presence of tides?
Present, sorry. Your voice is a little bit noisy.
Sorry, I'll just change.
Is your model assimilating in the presence of tides, or do you have, or your models don't have tides turned on?
Sorry, I cannot the meaning of your question, but I assimilate the sea surface height and other satellite data, and this is not include tide. This is not assimilate the tide gauge data set.
Okay.
What he's asking is, your model has tides switched on?
This model have not included the tide, but we can in the future, because we have a switch on and off this tide effect.
Thanks, Shun.
Okay, thank you. So we would like to move on to the next talk. So next is Areta from the University of the Philippines. The title is Biogeochemical Research in the Philippines, Effort and Expectations for the Ocean Forecasting Systems.
I can start now?
Yeah.
Okay.
but not sharing your slides.
Yeah, I'll share.
Yeah, please.
Okay. This is, you can see it? It's okay.
Yeah, perfect.
Okay. Thank you. Hello, everyone. So yeah, this will be a bit different probably from the other presentations in this session, since we're still far from these kinds of data assimilation systems. So this is just an opportunity to discuss some efforts and expectations in relation to biogeochemical modeling and ocean forecasting systems in the Philippines. And so just to introduce the Philippines, it's an archipelagic nation and with one of the longest coastlines in the world. And we have about 62% of our large population live in coastal areas, and while the rest rely on our seas in one way or the other. The ocean economy is estimated to provide about 7% of our GDP and employs about 5.3% of the total employment. The estimated value of the coastal and marine ecosystems are at about almost $1 trillion US annually. So the key economic activities that make use of the ocean are coastal and marine tourism that rely on the health of marine ecosystems, fisheries and aquaculture, providing food and livelihood, manufacturing, electricity, gas and water supply, and ports and shipping that provide supplies and infrastructure for important materials and enable various critical activities. So unfortunately, even as the Philippines is considered the center of marine biodiversity and is highly reliant on the health of its oceans, its seas are also highly threatened by local stressors such as overharvesting of resources, different types of pollution and coastal development, as well as the global stressor, of course, of climate change. All these issues only add even more to the fact that the Philippines is already a highly vulnerable country to disasters. So, climate change can exacerbate the intensity of these disasters, such as typhoons, which in turn impact the marine ecosystems and ocean economic activities. Another example of a climate change impact that the Philippines can already feel is coral bleaching as oceans warm up and also stratify. So the Philippines context thus makes it imperative that we are able to sustainably manage our marine resources and to manage our ocean-based resources for sustainable use and prevent and mitigate disasters at present and in the future. It is essential to have ocean observation, modeling, and forecasting capacity. However, these are sorely lacking, and from the physical infrastructure itself to the technical capacities. So in this talk, I will just give an overview of some general efforts towards ocean modeling and forecasting, primarily for research and some specific applications. Going forward, I'll be separating modeling efforts that are geared towards mainly just research and enhancing understanding versus those that are more for operational forecasting. So based on what I'm aware of, the government agency PAG-ASA, or the Philippine Atmospheric, Geophysical, and Astronomical Services Administration, would have the only system where atmosphere ocean models are operational in assimilating real-time data for forecasting. So they make use of the weather research and forecasting model, advanced research WRF model, with boundary conditions coming from the global forecasting system by NOAA. And they have a suite of automated weather stations and other observational systems that are scattered all around the Philippines, providing them the synoptic data. And PAG-ASA is more concerned with more atmospheric aspects. So of course you have daily weather forecast to some marine states and warnings for long-term climate impacts on agriculture. So I'll now provide examples of efforts towards more on the biogeochemical modeling for research purposes at the regional and local scales. At the regional level, there are a variety of studies that have used models to better understand the South China Sea region to the west of the Philippines. And similarly, different studies have modeled the tropical and Western Pacific region to our east. These have typically focused on productivity and biogeochemical cycles as impacted by seasonal and interannual variabilities, also impacts of upwelling processes, mesoscale eddies, typhoon disturbances, and climate oscillations, such as, of course, ENSO. Though these have coarse resolution for the Philippines and are mostly encompass just parts of the country, there are insights that can be obtained from these studies, such as monsoonal patterns and the typhoon and ENSO impacts on productivity and other ocean economic activities, which are still applicable to the country. At a more local scale, one example of a biogeochemical model was the one developed by Lermouchot et al. Sorry if I'm not pronouncing that correctly, but they make use of the MIT multidisciplinary simulation, estimation, and assimilation system capable of multi-resolution simulations over complex geometries with implicit schemes for telescoping nesting. They had from about 1 to 9 kilometer resolution in this work for the higher resolution models. So they coupled this to a biogeochemical model, and this was developed as part of the PhilEx project at that time, and they ran the model in real time for a few months. This was back in 2009, with only remotely sensed sea surface height assimilated every 4 days to about a week. And they use this to better understand the complex patterns and processes, especially through the straits and sills in the focal basins in the country. Another example is a model we developed to understand harmful algal bloom dynamics in an embayment named Sorsogon Bay that's in the middle of the country. And we coupled the 3D hydrodynamic model with a watershed and diffusion model, a population model for the focal hab species, and a shellfish toxicity model. So with this model, it helped us to understand the timing and the spatial hotspots for the harmful algal blooms and the factors that are contributing to the bloom initiation and decline. We also developed an NPZD model coupled to HICOM for the Philippine rice area in the northeast of the country. So this model contained 2 phytoplankton, 2 zooplankton compartments together with the other 3 nutrients and detritus. So you use this to understand that the patterns of productivity in this area and the contributing patterns, particularly the mesoscale eddies that are passing through there from west to east. For biogeochemical modeling efforts that are already being used for operational forecasting, well, I mean, I think it's just really global that can be applied to us. But so one example is the out of other models is the global ocean biogeochemistry analysis and forecast from the Copernicus Marine Service produced by Mercator Ocean. So it provides 10 days of 3D global ocean forecasts, updated weekly, including the fields of chlorophyll, nitrate, phosphate, silicate, dissolved oxygen, iron, primary production, phytoplankton, and pH as well. I think it uses satellite chlorophyll observations as part of its data assimilation. Of course, the resolution though is quite coarse, so about 20 plus kilometers, but it can be a starting point for initial national scale analysis of trends. For the local level, there's bank. So there's currently no biogeochemical model being used for ocean forecasting or even really a more operational, like dedicated ocean model for detailed marine forecasting. There are other model types that are currently being tested for operational forecasting for specific applications. So one example is CHABS, or the semi-automated harmful algal bloom detection system, which processes chlorophyll A concentrations from modus aqua and processes this to put out chlorophyll anomalies that can be used to warn of potential blooms. This includes a feedback system called Do You Habit, through which our program partners and other users can calibrate, validate, and improve the model forecast by zooming into their particular area and inputting data and information that would shift the thresholds for the chlorophyll anomalies.
5 minutes.
Oh, yes, thank you. We are also currently observing the performance of models for HAB forecasting at specific sites. So this is a machine learning model that we developed from historical data and makes use of real-time sensor information for the forecasts. It provides the likelihood of toxic blooms and fish kills, and is deployed in a very intensive mariculture area in the northwest of the Philippines, named the site is in Bolinao, Pangasinan. So as part of that HAB modeling and forecast system, an important aspect is that we are also building the historical ocean data in a standardized manner, which is quite lacking in the country. So these kinds of data sets, of course, as you know, are key in building up any sort of model, whether for understanding or for forecasting. So looking forward, there are definitely many needs. We need to vastly improve our ocean observational capacity, which is critical if you want to set up those ocean forecasting systems. Though due to limited resources, we, I think, need to understand the uses and applications of different levels of equipment for this. So for example, how can we harness and optimize more accessible, low-cost observational equipment considering their inherent limitations? We need to build capacity for people and agencies in different aspects, from not just the observational one, but also even to the modeling and analytical and forecast processes. Stakeholders should be more actively engaged, not only at the end of product development, but from the very start of the process. This would help increase buy-in, uptake of the tools, and enhance the sustainability of the tools and technologies developed. So in relation to this one, consideration is on how to also make use of data and possibly non-conventional information from local communities as part of data assimilation and forecasting systems. So suffice to say, we have before us many challenges and opportunities to develop ocean forecasting systems that can be especially useful for the country. And definitely this ocean decade is the time to really take these on. So with that, thank you very much for your attention, and hope to have good discussions from this.
Thank you. This is a very nice talk, I think. Any questions or comments? And if you have the questions or comments, please raise your hand, or please turn on your mic. And you can put on your questions. You can put your questions onto the chat boxes.
I think there's one.
Nadia, please, Nadia.
Yes, hi. So thank you, Aletta, for this very interesting discussion on the future of our biogeochemical forecasting. But just wanted to ask you, since in Europe, in CMEMS, we are for many years trying to evolve the biogeochemistry. What is, in addition to biogeochemistry, for the UN decade that you would think is a next step? So how do you go from let's say, zooplankton parameterized at the end of our models to higher trophic levels? Is that what we need to do? Or is there something else?
Well, I think so on the level of just this relatively simple, I don't know if it's really simple, biogeochemical modeling, one aspect is actually honing in on specific species within the plankton, because productivity is fine, but then some are like the HAB species are a hazard. So teasing that out within those models is something I think important, and especially now there's a lot of instances of HABs all over the world. And then the other, going up the food web, yeah, I mean, that is kind of like the whole ecosystem up to the higher trophic level. That would be definitely something of interest for many applications in terms of the fisheries, since that's really the one that's being harvested. But that's going to be quite tricky. But yes, that would be, I think, quite useful. Thank you.
And the one comment from the Emily, we are to the Nadia. We are nesting our regional PGC model into global model, some from the CMEMS, as Aretta described. It would be useful if the full model state was made available, so there is a more complete forcing data set available. Yeah.
If I might say one quick thing for Emmeline, I think that this is another topic in addition to Aletta's very important point that we need to have more details on the phytoplankton, for example. That's also a big thing. This is the other thing is a big data problem and transformation problem. So in CMEMS, we decided not to have a lot of parameters because of problems in data sharing and accessibility. So this is a problem that we need to look after in the decade. We have to think how to make more accessible the data. So very important point. Yeah, thank you.
Yeah. Thank you for your comments from Nadia. And I would like to move on to the next speakers. The next is Arya Paul from the INCOIS in India. The title is Regional Ocean Data Simulation System in the Indian Ocean.
Am I audible?
Yeah, I can see your screen.
Okay. So, hello everyone from India. So, I will describe about the data assimilation system that's what we use in INCOIS. So INCOIS stands for Indian National Center for Ocean Information Services. It's the nodal agency in India that is responsible for ocean state forecast and analysis. So India or INCOIS actually has two data assimilation systems. One is at the global scale, which is INCOIS GODAS, that uses the Ocean General Circulation MOM, and then it couples with 3D VAR. So like Shun was talking about 3D VAR. So this system is kind of more in line with NCEP GODAS. So this global assimilation system, this assimilates observations like temperature and salinity. So this global system, it provides boundary condition to a basin-wide Indian Ocean regional model, which is called ROMS LTKF or LTKF ROMS, where we use the ocean model ROMS, which is a sigma coordinate model, and it's about 1/12 degree resolution, about 9 kilometer horizontal resolution and 40 vertical levels. And the assimilation scheme that we use is LETKF, Local Ensemble Transform Kalman Filter. So this assimilation system in turn provides boundary condition to another high resolution model, which is about 2 kilometer resolution, which we call NIO HOOPS. So today in this presentation, I will focus mostly on ROM's LETKF. So the specifications that we have here is that this domain captures the entire Indian Ocean. Like it's from 30 south to 30 north and then 30 east to 120 east. And like I said, the resolution is about 9 kilometer horizontal resolution. There are 40 levels. And this is forced by atmospheric flux that we get from one of our sister agencies, NCMR-WF. So we have around 80 ensemble members of this system. And each of these 80 ensemble members is forced by different atmospheric fluxes. So all these different atmospheric fluxes, they also come from an 80 ensemble member system, a GFS model, data assimilation atmospheric system. So each atmospheric model kind of forces each ocean ensemble model. Okay, and we use kind of localization radius, something like 200 kilometers. And we also use a covariance inflation factor of about 10% to maintain the ensemble spread. So the observations that we assimilate are in situ temperature and salinity profiles from various platforms like Argos, mood buoys, ship tracks, etc. So in the left panel, you can see that is a plot of all those in situ profile data locations for about 1 year in this entire Indian Ocean domain that we have at our disposal. And then on the right hand side, I just show you a kind of an animation of the satellite track data from AMSRE of SST, sea surface temperature. So these are the data that goes into the LETKF ROMS system. So this is just a pictorial representation of how the system works. So there are 80 ocean models, each forced with a different atmospheric fluxes. So the global system gives us the boundary conditions, the INCOIS GODAS, and this system runs for 5 days. On the 5th day, the temperature and salinity and satellite SST of the 5th day only, not of the previous 4 days, only of the 5th day, whatever is available, we feed to the system. All these observations we feed to the system, we assimilate them, and then we provide forecast and analysis. Now, there are two novelties in the system which you will probably not find in other data assimilation systems to the best of my knowledge. So one novelty is that, so when we prescribe the representation error or the observation covariance error to the system, so one of the requirements of data assimilation, most of the operational agencies, they kind of, as far as I know, either provide stationary representation error, or the representation error varies across depth. But what we found is that if we can find a way, rather we actually found a way to estimate the representation error and the spatiotemporal variation, variabilities of the representation error, and we can prescribe it, then there is a profound improvement in the RMSDs. So in this plot, I'm showing you the time series of RMSD in SST. So what we see is that the purple color is the one in which the observation error covariance or the representation error, this has a spatiotemporal variation in X, Y, Z, and T. So this works actually best. The other novelty that we have in the system, and that is probably will raise eyebrows to eyebrows of data assimilation experts, is that those 80 ensemble members that we work with, we have kind of divided it into two parts, 40 members each. So 40 members, they respond to KPP mixing scheme, and the rest of the 40 members, they respond to another mixing scheme called Miller-Yamada. And we also kind of do not keep the parameters like the tracer diffusivity and the momentum viscosity. All these parameters, they are not same across all the ensemble members. They slightly vary. Now, we had to do this in spite of a covariance inflation of 10%, because what we found is that without this, we were kind of unable to keep the model ensembles from not collapsing. So that's the reason we did it. Also, this ensures that we get the benefits of both the mixing schemes. So our previous experience suggests that KPP mixing scheme, this works good in the North Indian Ocean domain, whereas the Miller-Yamada works good south of equator. So just to get the benefits of both the mixing scheme and to keep the ensemble spread from collapsing, so we used this strategy. But then this strategy has a caveat. The caveat is that normally in linear ensemble and in linear filters, one of the prerequisite is that the background probability distribution, it has to be Gaussian in nature. Now the problem is that with using two mixing schemes is that instead of it being unimodal, the probability distribution now becomes bimodal. But thankfully, the data assimilation scheme that we have, it takes care of that. Whatever bimodality or whatever deviation we have from Gaussianity, that deviation is small. And instead of getting adverse effects, we actually get a lot of improvements. So this is a plot of the ensemble spread for over 2 years. So the top two panels show a spatial distribution of ensemble spread for 3 such dates like 1st September 2016, 1st March 2017, and 1st September 2017. The top one is for the surface, and just below that is for the temperature at for the spread of temperature at 100 meter. And below that, I also show you a time plot, a time evolution of this spread. The blue one shows for the surface, and the red one shows for the subsurface. And we see that the ensemble spread is kind of remains. The mean of the ensemble spread kind of remains same, and it's kind of fluctuating about a mean. So we kind of managed to, using this strategy, arrest the ensemble collapse. So this is one of the analyses. I will not show you a lot of analysis that we have. For more analysis, you can always, over here, there's a technical document. You can always browse through this. But then on the left-hand side, I'll show you all the Rama buoy locations and the buoy and the ADCPs that we have. And from one of that at somewhere in the equator. So on the right-hand side, I am showing you the Taylor diagram of SST from there. And the triangle shows you for the free run. So when you do not assimilate anything, we have RMSD of more than 0.4 degrees centigrades, and also the correlation is somewhere between 0.7 and 0.8, and also the standard deviation is pretty far off. But whereas from Incois Godas, which is by the square dot, and the LTKF, which is like a circle, what we see is that because of assimilation, the RMSD comes down from 0.4 to 0.2. Also, the correlation improves. It improves to about 0.9, and LTKF it's almost close to 0.95, and also it gets the variability correct. So one of the independent variables that state variable that we analyzed was currents. So on the
3
right
minutes.
top, you okay. So on the right top, you can see the Indian coastline, and you can see a colored blob in the south, close to the east coast of India and kind of north of the Sri Lankan tip. So there we actually have an HF radar that measures currents, and the colored blob, the yellow blue colored blob over there, it shows the extent over which the HF radar can measure the surface currents. So over that domain, we kind of compared how a free run, which is here denoted by O ROMs, and how LTKF ROMs they fare. So in the top panel, we show you the correlation of the currents of the meridional current with the HF radar observation. So the first one is for the LTKF ROMs, that means where we assimilate temperature, salinity, and SST. The second one is for the free ROMs, where we do not assimilate anything. And the third one is the difference. So if the difference is in red, which indicates a positive, which means the correlation has improved upon assimilation. So what we see is that over most of the region of HF radar domain, the correlation has improved. The correlation of meridional current with observation has improved. In the bottom panel, we are showing the RMSC. So figure D, it shows the RMSD of meridional current from LTKF ROMs, E from the free ROMs, and F is the difference. So the difference is blue or the difference is negative. That essentially means that assimilating has improved. The RMSC in the assimilated product is less than the RMSC in the free product. And we can see over the entire domain of HF radar, the surface currents, the surface meridional current has improved. And along this location, most of the current is actually meridional current because of this East India coastal current and the seasonally reversing. Sometimes it goes towards the poles, and after 6 months, it kind of reverses and goes towards the equator. So
30 seconds.
yeah. So these are the references if you want to look into the work. And so whatever I have said is contained in these 3 references. And thank you for your kind attention. And let's have discussions. And if you have any questions, please.
Thank you.
Thank you.
Thank you for your interesting talks. So any questions or comments?
Okay, can I?
Yeah, please. Yosuke.
Yeah. What do you use your data assimilation result, ocean prediction result for? Do you use your result for fishery or some disaster prevention or something?
Okay, so this product that we have is used for things like search and rescue operations. Also, it is not yet operational, but we plan to kind of use it for potential fishing zones to help the fishermen. And also it helps all those, marine goers who venture out into the sea. They look into this product and they get to know the ocean currents and then everything for the fishermen and even the ship companies and all that.
Thank you.
Okay, any other questions or comments? I have one question. So I think you try to make a ensemble spread. You would like to keep the larger ensemble spread to avoid a filter divergence, right?
Right.
I think that there is you use the two methods to perturb the atmospheric forcing and use a different vertical mixing parameter.
We already have, the point is we already have.
Important.
Okay, so we already have the atmospheric fluxes that we have. So they are ensembles. So they are different from each other. That is point number one. And also we did sensitivity experiments and we found that to have a better spread, the use of two mixing schemes appeared to have a better spread than just the different ensembles of atmospheric fluxes. But then it has this other caveat of bimodal distribution. And therefore we need to have periodic checks. Since it's an operational agency, like we keep doing those periodic checks to see whether the deviation from Gaussianity isn't too much. That shouldn't be too much. As long as it is within some limits, it's okay.
Okay, thank you. So we would like to move on to the next speaker. So next is Emily Jones from the CSIRO, Australia. The title is an overview of the data assimilation activities in Australia with a focus on the E-Reef biogeochemical data assimilation system and its use in the management of the Great Barrier Reef.
Thanks, Shun. I'm just bringing up the presentation now.
Okay, so I'm waiting.
All right. Can you give me a thumbs up, Shun, if you can see it?
Yeah, this is perfect.
Great, thank you. So thanks for the invite to present at this forum. It's a really great opportunity to share some of the activities that are going on within Australia. There's a number of diverse groups that work on data assimilation systems from global through to regional applications. So I'll quickly introduce those, but I'd also like to spend a little time towards the end focusing on data assimilation activities in the Great Barrier Reef area, primarily because it's a particularly complex area to undertake data assimilation, but it's also quite representative of a number of complex areas that are in the Western Pacific. And there's a potential that some of the methods that we're using in the Great Barrier Reef could be generalizable to other areas. So I'd like to just thank all the folks in Australia who are nominated here as co-authors for their contributions to the talk. So in the Australian context, there's a number of societal issues that our operational data assimilation systems are used for. From a global perspective, they're used for everything from search and rescue purposes through to then providing boundary conditions for the regional systems. Around Australia, we've been severely impacted by marine heat waves. So there's been a substantial amount of kelp die-off in the temperate marine ecosystems through to coral bleaching in the various tropical coastal locations. This has impacts not just on the biodiversity, but also things like blue carbon, as well as some of the industries, especially tourism in these areas. So, there's a very broad range of impacts that these dynamics are having. And then we're also seeing that, more recently, things like the oyster industry are being affected by Vibrio outbreaks, say in South Australia, and that's also been linked to climate change. So whilst Australia is doing some assimilation systems at the global scale, we're also doing a number at the regional scale, and I've highlighted the geographic locations for those regional systems here in Aqua, and we'll do a quick zoom around the country. So starting at the global scale, both CSIRO and the Bureau of Meteorology are very active in the development of assimilation systems at the global scale. The operational ocean maps system is run by the Bureau of Meteorology, led by Gary Brassington, and that's based on MOM and it has a particular focus on the physics. So that's circulation, temperature, salinity, and sea surface elevation. The DA methods employed in that are Ensemble OI, which is an ensemble-based method. The sibling component to the operational forecast system is also a reanalysis system, and CSIRO, the institute that I'm from, curate the reanalysis system. And that's termed BRAN, the Blue Link Reanalysis System. That data is available via the HTML link there. The societal applications there around operational oceanography, but we also use this for observing system design and trying to understand, the typical ocean states and smart climatologies. So one of the exciting developments that's occurring as we speak is an upgrade to the operational service. So the Ocean Maps 4 is going live in February 2022, and that system is actually a full ENKF system. So it uses 48 dynamic members, and it's augmented with a further 144 static members. So we reduce some of the issues relating to ensemble collapse that Aria mentioned before. So that particular system has shown quite substantial improvements in predictability for sea level anomalies and some marginal improvements for temperature. So it's quite an expensive system to run, but the assessment has shown that it adds substantial skill to our current system. So zooming in on some other activities that the Bureau are contributing to. So they also have a regional system for the South Australian Gulfs. That's based on ROMs. It's also got WaveWatch 3 evaluated on an unstructured grid in that particular area. That particular application uses an ENOI system at the 2.5K scale, and then it's a free running 500-meter model nested within that. And the major application for that particular model is around the fisheries along the southern shelves of Australia. Ivica from University of Western Australia, he runs a number of ROMS-based systems, one for the Perth region and also one for the Northwest Shelf area. The Northwest Shelf one's shown at the top, the Perth region shown in the bottom there. Again, that has a focus on the physics. The methods used there are the 4D bar system. Again, the output around Perth is available through those URLs. And there, he's got a particular interest in, coupling with the atmosphere. So there's some tight coupling with a WRF model over the top of the Northwest Shelf model for extreme event prediction. But they're also interested in marine heat waves, public interest, for example, the Rottnest Open Ocean Swim. They use the Rottnest model to do trajectories to get you to Rottnest Island as fast as possible. And also oil and gas design criteria. The UNSW group, the lead contact there is Colette Carey. She has a ROMS 4D bar system set up for the East Australian Current area, again, physics. The particular applications that they're interested there are using some of the functionality of the 4D bar system to look at observation impact and observation system evaluations, so that we can try and understand, which are the observations which are contributing to the greatest constraint for various metrics that we might impose. And the one that is particularly dear to my heart is the E-Reef's prediction system. So the modelling side of that is led by Mark Baird, again at CSIRO, and the assimilation components of that is a topic that I lead. The modelling system here is EMS. It's an open source coastal modelling system that we curate in-house at CSIRO. It's available on GitHub, and it has coupled ocean sediment BGC wave libraries. And the assimilation system that we put over the top of EMS for both the physics and also the BGC, again, is an ensemble system, and we have both ensemble OI and ENKF systems ticking over. And that's used for annual reef health reporting, as well as trying to understand, what are the likely impacts of potential reef restoration interventions that might be imposed. So some of the actual uses for the E-Reef system that are particularly desirable for managers in this particular area relate to the annual report cards. So pre-2017, annual report cards for inshore water quality and ecosystem health were largely derived from satellite-based observations and a fairly sparse in situ monitoring system. And it was particularly problematic for this area because the waters are very optically complex. So traditional satellite algorithms such as OC3 and OC4 can't really detect chlorophyll. They're really affected by CDOM and sediments in the water. So regionally specific algorithms were required to be developed for this area. And also during the wet season, which is when we get the worst water quality in some of these areas, there's high cloud cover. So the observing system was not particularly sensitive to some of the changes in actual in situ chlorophyll changes. So the solution there is we've started in 2012 working on an assimilation system that combined in situ observations with remote sensing observations to come up with a 4D picture of the reef. And we then use that hybrid observational model product to then do the reef health reporting. So the current system is nested within a global suite of models. There's a bunch of catchment models that then force the rivers, as well as the loads required for the BGC system. Within the actual coupled BGC hydro BGC model, there's a number of optically active constituents. So one of the very unique things that we do within EMS is we actually predict what remote sensing reflectance at various wavelengths would be seen by a satellite at the surface of the ocean. And that enables us to assimilate remote sensing reflectance into the model to constrain the state variables of the model, which are then used to produce these report cards. So just to give you a taster for what we actually produce, we try and bring our model state, the diagnostics from our model as close to the observations as we can. So on the left there, we've got observed remote sensing reflectance at 3 bands, so 488, 547, and 667 nanometers. And then on the right, we've got a modeled remote sensing reflectance at that same band. And it's quite important that we predict the reflectance very close to the time that the observation was taken, so that things like zenith angle and viewing angle don't differ too much. So what we do is we make model data differences in the reflectance bands, and we use those innovations then to project onto the unobserved state variables via the background error covariances within the assimilation system.
5 minutes.
So to give you, thanks, Shun. So to give you a taster for what it looks like. So if we have a free run of the model on the left there, that's the October average chlorophyll in the surface. When we do the assimilation, we get this surface value for chlorophyll in the center there. And the difference is that the assimilation system is adding chlorophyll within the GBR lagoon and taking away chlorophyll in some of the offshore locations. Because we've got a biooptics model, we can also model water clarity, and we can look at differences in water clarity between the unobserved and so between the assimilated and non-assimilated model. And we use Secchi depth as a proxy for water clarity, and you can see the difference there. So the assimilation system reduced the water clarity in the GBR lagoon and increased the water clarity offshore. The other nice thing is because we've got an optics model there where we can combine wavelengths, we can also come up with something called simulated true color. So this is an example of where we had a plume of sediment in one of the coastal bays misplaced. The control run with no assimilation had that in the wrong location. However, when we assimilate the reflectances, it adds in suspended sediments, and we then get the plume in the right place in the simulated true color. So the consequence is from 2017 through to present, we now use the GBR reanalysis system to produce these annual water quality cards. And this is through this can now be accessed through an interactive portal through the GBRF. Sorry, Gabrumpa. So in summary, the Australian DA community uses quite a diverse set of tools, both models, from physics through to BG3, as well as assimilation systems from variational through to ensemble methods. The assimilation system summary for the GBR, we're using remote sensing reflectance. So this is quite a generalizable method, I think. We don't require bespoke regional algorithms for satellite ocean color to give us, estimates of CDOM and TSS and chlorophyll. We can back that out using reflectance with the model. The nice thing is the ensemble methods don't require the coding of the tangent linear or adjoint, so it's quite flexible and we can tweak the system fairly quickly. There's a real opportunity here because any RGB sensor that you might have on your mobile phone can be used to derive a remote sensing reflectance using software like Eye on the Water. So there's an opportunity for these sorts of systems to stimulate citizen science activities. And there also, we can use quite sparse in situ observing systems to then assess the model. So some opportunities that I thought, might come out of this particular incubator. There sounds like a lot of people are using ensemble-based methods, as well as, some of the 4D VAR methods can produce estimates of uncertainty. And we'd be really interested to know how others have been communicating estimates of uncertainty from their ensemble prediction systems to managers. And similarly, it sounds like there are a number of models running in the Western Pacific, and it might be exciting if we all made our ensembles available when data, big data issues allow us to, because if we've got ensembles of models, it means that everyone can start nesting their own systems within other ensembles to look at, real uncertainty as it propagates between different levels in the hierarchy of models. Here's some references and also links to the software, and that's pretty much it from me. Thanks very much.
Thank you. Thank you for a nice talk and nice suggestions for ensemble, providing the ensemble to the managers. Yeah, so any questions or comments? So please, Naoki.
Yes, I have one. You have actually what your colleagues are doing actually. For example, 2 universities already running the coastal models in operation. Maybe they are using ensembles from your association, I mean CSIRO or.
So I think Ivica is certainly running his Northwest Shelf model and also the Rottnest Island model, operationally. I don't believe he's nesting within the models that CSIRO are running, but I think he certainly is nesting within some of the Bureau of Meteorology models. So, but at the moment, the Bureau of Meteorology is running Ensemble OI, which is not, they don't make available the ensemble, obviously, from ENOI, but when we go to Ocean Maps 4 in 2022, that ensemble may become available.
May I ask some money question? For me, the university, it's very difficult to keep the model running for operation. Are they all, getting the research fund at their own effort from the local company, or are you guys Bureau Meteorology or CSIRO supporting them, the activity?
The funding structure in Australia is challenging at times. So Ivica, I believe, works closely with some of the oil and gas companies on the Northwest Shelf. So some of his operational work, as well as prediction systems, are funded by oil and gas. Colette has been funded, I think, through various postdocs. So you're absolutely right. There is difficulty in funding. However, the compute that's used to effectively turn the models over, that's made available through a merit allocation scheme on a number of the supercomputers that we've got here. But no, I certainly don't have a silver bullet for the funding issue. I'm sorry.
Thank you very much.
Okay, so next is Nadia.
Is it for me time to present?
No. So
okay.
I see
a question. Yes, a question. Yeah. So this is a very important question, I think, to consolidate operational oceanography and somewhat prevent us from doing the same errors that Met offices did like 40 years ago. So we have to preserve a very tight connection to the research community while we develop operational oceanography and operational systems. So we have to foresee from the beginning that there is substantial funding for research on operational systems, on models, and so on from the start. So it's okay that our university will start running an operational system. This is not going to be probably the end of that, but it's definitely a very important test case that would be most likely be taken by some agency when we will have operational ocean agencies, maybe together with Met offices. Every country will do it differently. But we should really value that universities do develop operational systems or pre-operational systems, if you want, and try them on the real time. And there are several issues that are connected with the real time that cannot be spot from a delay mode experience. So I would say oceanographic community should really value a very tight connection between university and growing operational oceanographic agencies.
I'd agree with that, Nadia. And I also think that there's this kind of canyon of death between a technical readiness level 8 system that might be pre-operational in your university to then transition it to a technical readiness level 9 system that is supported 24/7 within an operational agency. Because going from that TRL8 to TRL9 system, there's a huge support base required for that. And we should absolutely value the TRL8 systems, I think, that we have going around, because they are the precursor, the leader for what might be possible at the TRL9 level at the 3 to 5 year time horizon. So yeah, I agree with those comments.
Okay, so thank you. So we move on to the next. Next is Vinay from the Indian Institute of the Science. The title is the Introduction of the ForeSea.
Thank you, Dr. Oishi.
Yeah.
I shall share my screen now.
Yeah, please.
Okay.
Yeah,
So,
but this is a presenter mode, not presentation mode.
yeah.
Yeah, it's okay.
Hello to everyone, and a very warm welcome to this short presentation on ForeSea. Ocean prediction is an essential component in the provision of dissemination of ocean information, and OceanPredict is a science program for the coordination and improvement of ocean forecasting systems. OceanPredict provides a platform for communication and knowledge exchange. OceanPredict is run by scientists and experts in operational oceanography from around the world. And the goal of OceanPredict is to accelerate, strengthen, and increase the impact of ocean prediction. ForeSea, the ocean prediction capacity of the future, is a UN Decade of Ocean Science program that contributes to the decade goal of a predictable ocean, where society has the capacity to understand current and future oceans. The vision of ForeSea is for strong international coordination and community building of an ocean prediction capacity for the future. There are two overarching goals. The first is to improve the science, capacity, efficacy, use, and impact of ocean prediction systems. And the second is to co-build a seamless ocean information value chain, right from observations all the way to end users for economic and societal value. These transformative goals aim to make ocean prediction science and in order to extend the vision and transform the capacity of ocean prediction, we have certain high-level objectives. These are listed here. The first is to coordinate ocean prediction worldwide in a suitable manner towards maximum societal benefits. The second is to maximize the benefits of ocean observations for ocean predictions and societal impact. The third is to support development and maturation of the full-length operational oceanography value chain from observations to the end users by using best practices and coordinating the integration of existing and new partners, such as international science initiatives and intergovernmental organizations. The fourth is to advance the science behind ocean prediction and its connection to the other components of the Earth system, which includes atmosphere, land, cryosphere, continental hydrology, etc. Finally, make ocean prediction science more impactful and relevant by collaborating with the socio-economic experts and stakeholders to quantify the impact and utility of ocean prediction for science and society, especially in coastal areas, particularly in collaboration with CoastPredict, which is another UN decade program. What is envisioned? It's envisioned that ForeSea would transform the ocean prediction so as to penetrate the layers that have not been accessed until now. Towards this, ForeSea will co-create a framework for operational oceanography, enabling scientists to engage and collaborate with all components of the value chain, as well as the UN decade programs associated with these components. This would enable the creation of an effective and sustainable operational oceanographic ecosystem environment, which is responsive to user needs. More importantly, ForeSea will enhance communication of the impact and relevance of ocean prediction. Outcome from ForeSea is expected to improve the interaction between the ocean environment and society, particularly in the areas of human health and health of the environment. Having a good understanding of the oceans and their interaction with the human health will be important in any future human health disasters. The improved integration of observations and models, which would happen during ForeSea, would allow science, policy, and civil organizations to understand the ocean's role in health impacts, especially under a changing climate. Accordingly, the emphasis of ForeSea will be on making the ocean predictions and reanalysis easily accessible to community at large via a central repository. In order to approach the solution, ForeSea will focus on two major themes. The first theme is catalyzing transformative ocean prediction science solutions for sustainable development, connecting people and ocean prediction. And the second theme is increasing impact and relevance, improving science and science capacity for the ocean we want. Realization of these themes would take place through projects that take up the challenging task of scientific development demanded by impactful and relevant. Connection and exchange with other bodies is absolutely essential to achieve these large goals. Democratizing ocean information to enable more impactful engagement is not an easy task to be achieved alone, but together with other forums of similar interests. ForeSea will collaborate with and leverage data access platform programs to provide inclusive accessibility ease to ocean observations, ocean prediction inputs, and ocean system information. This would be done in an equitable manner, enabling everyone to access and benefit from ocean information. In addition, ForeSea would engage with the diverse stakeholders in the co-design processes via existing or emerging partnerships with programs such as UNEP, GeoBlue Planet, WMO, IOC, and GOOS, and also with other DGATE programs such as CoastPredict and Marine Life 2030. Larger participation from the scientific community will be solicited via projects that are. The email contact point for ForeSea is ForeSea2020@gmail.com, and the webpage is oceanpredict.org. Thank you very much for your attention.
Okay, thank you for introducing the ForeSea. So any questions or comments? The quick question is prepared. Okay, so we move on to the next speaker. Next is Nadia. The title is Introducing of the CoastPredict.
Thank you for this very interesting meeting. I will not be very technical today, but I will try to show you the main concepts behind our starting of a UN decade program called CoastPredict. This is work by, as chairs, myself, Vili from University of Miami, and Joaquin Tintoré from the Balearic Island Observatory, but many other people have greatly contributed to the starting success of the program. So we are co-designed with GOOS from the start. We tried to get into the proper communication with the UNESCO program jointly with WMO that will at the end be able to internationalize and structurally change our way to work in operational oceanography. And so we work together with Ocean Observing Co-Design that is mainly devoted to open ocean observations, but then also starting to get the coastal part, and Observing Together, which has the stakeholder involvement. We are here at CoastPredict clearly. So CoastPredict, first of all, would like to have a science transformation process. As you know, the coastal ocean has different interpretation in different countries, in different science groups, and we would like to advance what in 2010 was a definition given of the global coastal ocean. So we try to think that there is a definition of the global coastal ocean, and the proposed starting definition is the one of a large area that encompasses the land and the ocean as much as is required, and we think that CoastPredict will contribute to a scientific redefinition of the global coastal ocean. So CoastPredict will try to apply the 21st science paradigm to the global coastal ocean. What is it? Is systemic ocean science, which includes the observing system, the numerical models, and the data assimilation. We have seen wonderful examples here with uncertainty estimates, and the holistic and convergent ocean value chain, which will show how much is needed to arrive at customized products and services, going from observing systems to forecasting information services to customized products and services. And after this, clearly, we are all devoted in the UN decade to have new science-based information for sustainable development goals targets. So why CoastPredict? This is the latest IPCC Working Group 1 Sea Level Rise Assessment. And you see here the big boxes where sea level rise is assessed by the multi-model approach, IPCC multi-model approach. It's clearly too coarse to resolve the regional local scales. We have to really find standards to downscale this. Furthermore, as you have seen here, we have to standardize the way to arrive where the people live with our forecast. And this is an example. Okay, we can stop here. So we know, as we have seen already from other presentation, we have now reached a kind of maturity in our downscaling to the coast, but we have to make this accessible, shareable. As Aletta said before, we need to involve and grow capacity in agencies and scientists to use this data, in addition to building the data sharing infrastructure that allows everybody to build coastal models of this kind, go into the real problems in their coastal areas. Sorry, I missed. Okay, so high level objectives of CoastPredict are a predicted global coastal ocean with this new vision that solutions could be shared across the coastal ocean, the upgrade to a fit for purpose oceanographic information infrastructure, which we hope to do with ForeSea for the open ocean part, co-design and implementation of an integrated coastal ocean observing and forecasting system. And, you know, with best practices and standards. In oceanography, we have very few standards, little bit of community of practice, mainly. Okay, so our new, we have been endorsed on the 8th of June. We have been working to see how to implement our ideas in a way that is close to the research, and then will give substantial changes at the end of the decade. So we have now found 6 focus areas. The first one is short-term coastal forecasting and early warnings. Second one is coastal climate monitoring, downscaling. Third is solution for integrated coastal management, coastal ocean and human health, international open and free access to coastal information, and equitable coastal ocean capacity. This we would like really to develop with all the other programs that have components that are interesting. Our strategy at the moment is to build core projects in each of these 6 areas that will have a sub-projects, smaller ones, but generally core projects that can be amenable to more general and standardized, at the end have standards to be taken at international level. So now we are at the point of formulating with and enlarging the number of people involved for this core project, answering to the third decade call for actions. So here is our group. We hope to grow much more. We are, still very few with respect to the complexity of the problems at hand. We will have our first General Assembly soon in December. Please contact us at info@coastpredict.org. Thank you.
Thank you for introducing the CoastPredict. So any questions or comments? Okay, so we would like to move on to the discussion part. So unfortunately or fortunately, thank you for many questions and comments. So the 25 minutes, only 25 minutes left. So I would like to baton touch to the Vinay. Okay.
Yeah, sure. Thank you, Dr. Hish, for giving this opportunity to chair this discussion. So my name is Vinay Chandran. So gently I'm known as Vinay because my name is a bit long. So you all can call me Vinay. I'm a professor of oceanography at the Center for Atmospheric and Oceanic Sciences of the Institute of Science, Bangalore. My expertise is in both ocean modeling as well as conducting field experiments on shipboard programs. I'm a co-chair of the OceanPredict along with Fraser Davidson and Eric Jassine. I'm also a member of the advisory committee of CoastPredict program, which is being led by Professor Nadia Pinardri. Today's topic is towards the societal applications of ocean data assimilation and forecast. Now, we all agree that the data assimilation is a very important component of any ocean prediction systems. It is essential to have an excellent data assimilation program in order to arrest the growth of errors, to create nearly true initial conditions and provide forecasts. Now, in the context of ocean decade, it also finds relevance into many other issues, such as extreme events. Oceans are subjected to various types of stress, such as marine heat waves, and there is deoxygenation, acidification, and also many coastal impact like coastal inundation, damage of coral reefs, and flooding, and so on. So there is increasing demand that is coming towards ocean forecasting systems as well as to ocean data assimilations. So today, in order to discuss these issues, we have several experts. I think you have met them already, but I would just like to introduce them briefly once again. And to begin with, we have Professor Nadia Pinardri. She's a full professor of oceanography at the University of Bologna in Italy. Her expertise is in open ocean and coastal observing and forecasting, as well as forecast applications for contaminant dispersion at sea and ship routing optimization. She is a member of the strategic board of the Italian Centro Euro Mediterraneano sui cambiamenti climatici. I hope I have spelled it right. Its abbreviation is CMCC, where she coordinates operational ocean forecasting and local Earth system climate downscaling activities. She is chair of the UN Decade of Ocean Science for Sustainable Development endorsed by program CoastPredict. And next we have Dr. Aleta Niguez. Aleta is a professor at the Marine Science Institute, University of the Philippines in Diliman, where she leads the lab of biological oceanography and modeling of ecosystem or biome. Her research focuses on understanding and simulating population to ecosystem dynamics in relation to productivity, harmful algal blooms, and fisheries. And she works on providing tools to enhance decision support for resource management. She currently serves as scientific steering committee member of the IOC and SCORE-supported Global HAB, as well as the IOC subcommission for the WESTPAC HAB and East Asian HAB. She's also scientific steering committee member of CoastPredict, which is a UNDCAD-approved program. We have Yusuke Tanaka. He is a CEO of Oceanized Company Limited. I think we have not seen Tanaka-san yet. So can you please switch on your camera?
Yeah, just I see.
Okay.
Just I can see the Tanaka-san.
Okay, I am unable to see. Okay, fine. Dr. Tanaka is also a guest engineer at JAMSTEC, and he funded the company with his colleagues in JAMSTEC and Kyoto University to implement the result of research for the actual economic world. His area of expertise is the generation of value-added information for activities on the ocean using the coastal ocean modeling products. We have Emlyn Jones, senior scientist with CSIRO at Hobart. He leads the coastal hydrodynamic modeling team and the marine environmental prediction and informatics domain. His background is in coastal modeling, and he has a keen interest in developing data assimilation systems for high-resolution hydrodynamic and biogeochemical models that inform management and policy decision makings. Finally, we all know very well now already, Dr. San Uhishi is a postdoctoral researcher in data assimilation research team in Riken, Japan. His research focuses on data assimilation and mid-latitude air-sea interaction using dynamical and heat and salinity budget theories. He is now developing an ENKF-based regional ocean data assimilation system and creating ensemble research analysis products in the Western, North Pacific, and maritime continent regions. It's a warm welcome from me to all the panelists and also to all the members who are attending this conference. Now, in order to take this discussion forward, I would like to invite each one of you to give your short general remark on the theme of today's discussion, that is towards the societal applications of ocean data assimilation and forecast. And then after that, I would like to take this panel discussion forward with 2 or 3 very focused questions, right? Right now, I would like to invite the panel members. May we begin with Dr. Nadia Pinardi? So what we would expect from in this round of discussion is your general comments and remarks towards societal applications of data assimilation and forecasting systems.
Thank you. This is a very important topic, and we know that we have to, well, we have already seen many examples in today's presentations. We really have to build on the success that we had in the past 20, 30 years in oceanography. We have now a system, an integrated modeling and observing system gives us science-based information for all sorts of applications. And we, as we said, we have seen, we have to continue and make this to be with more better standards to help many more people to use that effort. We need to develop observing systems that will be more and more tailored to the integrated observing and forecasting system in operation oceanography. Up to now, we have used, apart from satellite, mainly and Argo, I would say, data of opportunity. And then we have to build overall the data sharing infrastructure that will allow full use of this information toward the targets of SDGs. So at the end of the decade, we hope through the GOOS leadership to build a new program at UNESCO IOC where the data sharing infrastructure is available for all member states, for all research and agencies responsible for implementation of protocols for protecting the environment, the marine environment, and reacting and adapting to climate change. Thank you.
Thank you, Nadia. Dr. Yusuke Tanaka comes with a unique experience of having interaction with both academic community as well as industry. So next, I would like to hear from.
Thank you. I'm very interested in the presentation and the one other private company distributing the ocean information to the users, especially for the fishers. I would mention that data sharing is very important to share the distribute the ocean data, because we use the ocean observation data and we run the models and estimate them and generate the value-added information from the ocean model outputs. So basically, the stakeholders or users have no ability to use raw data. So we must generate the product from the raw data. So very important thing is to capability of use. One very important thing is to use the data. We can access the data and we distribute them. We can distribute. So the discussion on the speakers mentioned that operational oceanography value chain or democratize the ocean data. I think it's a very important point on today. Today I here. So
yeah.
thank you.
Sure. Yeah. Thank you. So you have shared a very important point, which is also being raised by Professor Nadia. Let's now hear from Dr. Aleta Negas, her introductory remarks.
Thank you. This has been quite an interesting session for me. I think it's exciting to see the many potentials and avenues. I'm learning a lot. And I think for us, where we are now here in the Philippines, as I said, there's a long way to go. But it was interesting for me to hear about what Nadia was saying about the link between the research activities and going to the more operational aspects, because I think that would be crucial for sustaining, of course, all these efforts. And on our side, I'm from a research institute, so we are still building up these kinds of studies for us. And although we are linking with the fisheries agency, they actually don't have the capacity to do these kinds of modeling. And so I think it's important to show, I don't know, it's probably applicable to other countries as other more developing countries as well, as to show how these kinds of information, data, and models can really be useful, because I don't think there's that appreciation yet for the significance of these kinds of outputs and models. And so if we build on that, if people can recognize that, if agencies can recognize that more, and explicitly see how these can be very used relatively easily or properly, then there might be more support for at least for efforts, for our efforts like this. So that was one thought. So I think I hope we can further our learnings and what we can show to here in our agencies and stakeholders from what has already been done in the other countries, like what you have done. So thank you.
Yeah, thank you, Alita. So you have raised a very important point on demonstrating how the ocean forecasting products have to be demonstrated for the end users, such as fisheries. So we will come back to that issue later. So let's now invite Emlyn Johns from Australia.
Thanks, Vinay. So thinking about the topics that were covered, you know, we saw presentations from a very diverse set of geographical domains across the Western Pacific and Indian Ocean. And, you know, thinking about what's actually required to feed into understanding sort of the decisions that managers and policymakers will make around the various SDGs, I actually wonder whether there's an opportunity and a gap that kind of needs to be filled between the sort of the physics and the fisheries management that ends up going on, because our assimilation systems, you know, they do quite well at constraining the physics within the ocean models, and you know, we're progressing, you know, quite well down that path. I'd say the BGC assimilation is probably less mature, and then, you know, as those systems start being used at higher trophic levels and in more complex examples to start feeding into some of the SDG decision making, you know, we sort of haven't, or at least I haven't seen too many examples, even within the MEAP task team within Ocean Predict, where assimilating BGC models have started being fed into, you know, ecosystem models or fisheries decision making and things like that. So I think there's a real opportunity in this space, but in a way it comes down to, you know, people. So I think, you know, data assimilation is a fairly technical, you know, discipline. And I think as part of this UN Decade of the Ocean, if we can shine a light on the fact that, you know, we really need practitioners that are willing to understand the subtleties of data assimilation systems, and not just continue on in the physics DA, but also in the BGC DA and the higher trophic levels, then you know, if we can make that exciting, then I think we might start seeing, you know, some more training opportunities coming up to entrain folks into those, you know, areas where we don't have a lot of people working at the moment. So, you know, I came away from this thinking, you know, we've got some great assimilation systems and prediction systems that do the physics. There's less assimilation systems that are doing the BGC, and there's even fewer that do the higher trophic levels. And, you know, I think that's a real opportunity going forwards. Thanks, Vinay.
Yeah, thanks, England. So you have brought out a very important issue, that is the need to go from biogeochemical modeling data assimilation to higher trophic levels of fisheries. So which would certainly have a definite impact on the societal aspects of oceanography. So next, I would like to ask Ohishi-san.
Yeah, thank you. And I would like to say the thanks for all the speakers and panelists. And considering the two other social applications, so I think that there are still a gap between the researchers and the users and stakeholders because they are lacking and the system to provide the output from the data assimilation system is now still lacked. So in Japan, the Oceanized here, the Yusuke Tanaka-san is here, but the venture company is just started. But this is only in a few years. So considering the Southeast Asian region, there are, I think that there are few companies to share in this ocean information to the users and stakeholders, I think. So this is the reason why I visit Yusuke Tanaka to these sessions.
Okay.
This is my comment. Thank you.
Yes, thank you very much. So I see several points which all connect to the same goal that has come out of this discussion. On the one end, we need to have a better observing systems. And in the next level, we used to have a better data sharing system. And we also should be able to enhance or widespread the capability to use their data. And in some cases, like where this information propagation is not efficient, we might have to even demonstrate how the data can be used. This is particularly true for fields such as fisheries. In order to achieve all this, there has to be additional technical development of the data assimilation system, such as extending them to higher trophic levels and fisheries and so on. So I think we have got a very good set of nice points for taking this discussions ahead. So these are very important points. But since our time has been shortened a little bit, I would like to come back to the main goal of our meeting, and that is how we can contribute to the overall goal that have been projected by large programs such as ForeSea and CoastPredict, and within the context of West Pacific regions, and also focusing on the application of data assimilation systems. So the idea is to get an idea on, because one of the things that we need to do is to co-design and take part in the co-production with the various stakeholders and partners. And these stakeholders and partners need accurate information on both coastal and ocean prediction. And this involves, of course, fisheries, shipping companies, and marine industries, to some extent, the marine pollution and so on. So I would like to invite your views on how this can be taken ahead in the context of WESTPAC ocean regions with respect to the application of data assimilation systems to ocean forecasting. So I think we would be right in begin that discussion with Aleta, who has already having some experience and expertise in this applications in this region.
Yeah, so well, the forecasting or aspect that I'm involved in is in terms of the HABs, not a mechanistic model, but the statistical model so far. But it would be, I think, of course, it would be of interest to. We started out with a mechanistic, but then found out that it's, of course, it's more data intensive, so it's difficult to make that operational. But that would be something that we'd be very interested in terms of the BGC models and specifically going into more the I know it's of interest for in terms of the fisheries grounds and also the HAB threats. So these that would be a key avenue, I think, that we see ourselves going into for this.
See, one of the projects, I mean, one of the proposals that we have seen, which has been tested, is to use shipping vessels to collect the data themselves, so that we get the data from larger data, and also we get the data at the locations where the fishermen actually go for their catches, and then it would also feed back into these regions. So there have been some tests and some presentations about this such a plans. So what is your view in terms of implementing such a program at a large scale for the WESTPAC region?
I think this could be promising because this is a big shipping transport area. And so there's a lot of potential for that. And even within the Philippines, the ferries, the passenger ferries, apart from cargo, there's a lot. So that could be that is something that we have thought about, but we haven't actually pursued yet. But
that actually also pertains to the issues of equitable ocean and also going back to the observing system. So Nadia, what would you think about I mean, further in this direction?
You mean me? You're asking me?
Yes,
thank you.
Nadia, yes,
yeah, sorry, I didn't get that. We tried in Europe, for about 2 decades to start up a fishery observing system, which was mainly France and Italy, I would say. And we found the pros and cons. The data are, very specific, meaning that you have sensors attached to the nets and you can collect a certain amount of data, which actually is useful. We actually assimilated these fishery observing system data, and they were useful. If somebody needs the paper, I will send it. They can contact me. But one thing I would say is ship of opportunity is something that is difficult to implement. It's very complicated. You have to make agreement with the consortia, the fishery consortia. They have to overlook the implementation of the sensors. It's a bit complicated. I would go, if possible, but this is also to be tried. Again, maybe when we did it, we didn't do it properly. I would say that we could try with more autonomous, continuing with the autonomous kind of robotics that will help us in the open ocean, for sure, and in the coastal, also with new autonomous systems and maybe drones that will help us to really monitor where we want. So I think that there are new parts to this, and hopefully ForeSea and CoastPredict will explore the new technical options. This is also an aim of the decade, that we have to bring some technology to the level of global implementation. So I hope, yes, we will start again, maybe the fishery observing system, and evaluate it again, but then also look for more higher, more advanced technology. So
thank you. Ohishi-san, how much more time do we have?
I don't know.
Okay.
So can we continue this session? administrator?
Well, probably we can take another 5 minutes or so.
I think so.
So I would like to invite
possible.
a quick comment from Emlyn about how, because Emlyn has already raised important challenges for data assimilation to societal applications. So I would like to know your response on how how we can take this ahead in order to contribute to the efforts of CoastPredict and ForeSea in terms of co-designing and co-production of new results.
Well, I suppose I'd just like to support Nadia's suggestion for autonomous observing systems, because I think there's a real exciting component there that would allow us to do adaptive sampling, which is particularly important, as quite uncertain ocean dynamics start evolving. So I would totally support that idea if that can get off the ground. But secondly, I'd also point out that, it's expensive to run global models. And, I'd just like to, I suppose, highlight the fact that, CMEMS has been such a fantastic resource for folks to, nest regional models within. Mm-hmm. So I wonder whether or not there's a real kind of, I wouldn't ever call it low-hanging fruit, but having something like CMEMS, but for this region of the Western Pacific, or even more broadly, allowing people easy access to initial conditions and boundary condition data, as well as fairly consistent and quality controlled observation data streams. If we've got those two things, then we're actually a long way towards having quite skillful regional models. So again, I hate to refer to it as low-hanging fruit, but I think that is certainly one of the first steps towards having a bunch of regional models that can then feed into societal applications.
Thank you. So one of the programs, one of the projects that would be part of this whole exercise is Synops from Japan, which is led by Yosuke Fujisan. So in that context, Ohishi-san, would you like to make a comment, a remark, and express your views on how this would be able to connect with our goals of data assimilation and observing system evaluations?
It is a difficult question, an important question, I think. So as mentioned by the Nadia, so the coastal application is more important, I think. And now the fisheries and the shipping companies can provide observation, but this is there still remain a problem due to technical issues to observe the insight data set. The insight data. So, but as shown in my presentations, the Kyushu University starts the new project to collaborate with private companies and fisheries, and they invent the new CTD, easy to handling for the fisheries. But there are like a tentative and test case, and the most difficult is to obtain the understanding from the fisheries, because they have territories in the coastal oceans, and they could not understand easily to what is the data assimilation, what is the prediction systems. So the spread in the value of the data assimilation is now still difficult, I think.
Yeah, thank you. So because of shortage of time, we wouldn't be able to go for another round. However, I would like to invite any comments from the attendants, participants of this meeting. If anybody would like to make a comment or ask a question to any of the panelists, we could admit 1 or 2 quick questions. If anybody is interested.
I see the comments from the Taco De Bruin.
Okay.
As IODE co-chair, I fully agree with the remarks made previously about the key importance of sharing data and information. I would like to point to the very successful pilot studies within the Ocean InfoFab project, OIH, with
Okay.
building an operational digital ecosystem.
Yeah. Thank you, Taco D. Bruin, for sharing this link, which has already linked to a successful program. Is there any other comment or questions? Nothing. So I think we had a very lively discussions, and several important points have emerged from different parts of the world and also from different forums. So these forums do pinpoint on the need for systematic observations which are autonomous, and at least to begin with, not to be not to be given to fisheries community for the data assimilation. Should be handled by the scientists and the governments. That's what I understand. And also there are technical difficulties in convincing the fisheries community in this. Moreover, there has to be a system by which data has to be quality controlled. It has to be reliable, and there has to be standards, and it has to be shared, and it has to be easily accessible. And this is a common point which has emerged from all panelists. And there is also a need for developing additional science and techniques for the ocean data assimilation systems. Of course, if we had time, we could have discussed a little more and how we can transcend what we generate to the level of social application. So probably that would have to wait for another panel discussion or forum. So let me take this opportunity to thank each one of you for giving your ideas, suggestions, and very actively taking part in this panel discussion. Thank you all. Over to you, Hishi-san.
Thank you for joining these sessions. Yeah, so we close this session. Thank you.
Thank you.
Thanks, everyone. Bye.
Yeah, bye, everyone.
Thank you, Vinay-san.